So looking back at this image just for a moment from the previous page, we can see that x bar minus 2 times the standard error was our lower bound for this confidence interval. And that x bar plus 2 times the standard error was our upper bound for this confidence interval. And we can see based on that that it makes sense to say that the margin of error, which we call ME, is equal to 2 times the standard error, which we refer to as SE. So this is a formula for margin of error given these circumstances, the circumstances being a bell-shaped sampling distribution and a 95% confidence interval. So we summarize that here under confidence intervals. We say sometimes we're given a margin of error in a sample statistic. If we're given a margin of error, all we have to do is add and subtract that margin of error to find the upper and lower bounds. If we are not given a margin of error, that's when we use this formula. We say that the margin of error is equal to 2 times the standard error, provided that we're talking about a 95% confidence interval and a bell-shaped sampling distribution. So we'll use this formula, ME equals 2 times SE for this situation, 95% confidence, bell-shaped sampling distribution. So looking at an example of a study, we have our Nintendo and laparoscopic skills study coming up again. This involves 42 medical residents, some of which were told to play Nintendo Wii for 1 hour a day, 5 days a week. So that was my treatment group. And then others which were asked to refrain from video games, which would be our control group. So this is an experiment because the researchers told the medical residents whether to use the Nintendo Wii or not. We didn't just track video game use, we controlled the video game use. We're going to go ahead and find a 95% confidence interval for the difference in mean improvement times. So we're given improvement times. We've got that the mean improvement time was 132.2 seconds for the treatment group, and it was 59.7 seconds for the control group. We're also given an estimate of the standard error. 25.4 is what I'm going to use as my standard error SE in this formula. So putting everything together, what we want to start with is our sample statistic. Since we're talking about a difference of means, the sample statistic is a difference of sample means. And we're going to call that XT bar minus XC bar. So that's the mean improvement time from my treatment group minus the mean improvement time from my control group. And to get that, I simply subtract the two values I'm given, 132.2 minus 59.7, and that comes out to be 72.5. Next, I calculate my margin of error. I'll call that ME, and because this is an approximately bell-shaped distribution, we're told that we can assume that, and we have 95% confidence, we can use the formula that the margin of error is twice the standard error. So I get my margin of error very simply by doubling 25.4 to get 50.8. Now my confidence interval is the sample statistic plus or minus the margin of error, and this 72.5 is my sample statistic. So I'm going to set up for this computation by saying 72.5 plus or minus, like saying give or take, 50.8. I will subtract to get the lower bound, and I will add to get the upper bound. I'm going to put these together in parentheses, starting with my lower bound, 21.7, and going up to my upper bound, 123.3. So this is the notation that we use to express an interval. Make sure that you put the lower bound first and the upper bound second. It's not valid notation if you write it in the other order. So it always goes lower, comma, upper, even though the way we talk about it when we say plus or minus, the plus is actually the upper bound, so it kind of gets us thinking about the upper bound first. So in keeping with that idea of plausible values, this is now my plausible values for the population parameters that we're estimating. So this interval describes the plausible values for mu sub t minus mu sub c. Well, we want to think for just a moment about what those mu sub t and mu sub c really are. It's something that's easier to talk about than it is to write in this particular case because we don't have a random sample of a population. So it's not all that clear when we start talking about what the population mean is versus what the sample mean is, just exactly what we mean. This population is hypothetical. We did work with 42 medical residents, but they were not a random sample of 42 medical residents. So it is reasonable that our population involves medical residents, but it's not clear that we can say this absolutely holds for all medical residents. What we do think is true is that the mean improvement time, the difference in mean improvement times between playing Nintendo Wii and not playing Nintendo Wii for a population similar to this group would be somewhere between 21.7 and 123.3 seconds. But it does not mean that this is necessarily true for all medical residents. So continuing with this idea of plausible values, we'll now go on to the next question. Is it plausible that improvement times would be the same under the two treatments? So what we're really asking here is it plausible that mu sub t is really equal to mu sub c? Well, if mu sub t were equal to mu sub c, then mu sub t minus mu sub c, which is what we have a confidence interval for, would equal 0. So this question is equivalent to asking, is 0 in the confidence interval? Anytime we have one of these questions about whether something is plausible, we want to figure out what value it is that we're checking to see whether it's in the interval. In this case, our interval starts from a positive value and it ends at a positive value. For 0 to be in this interval, it would have to start from a negative value and end at a positive value. So 0 is not in the interval, and therefore the answer to this whole question has got to be no. Because 0 is not in the interval, it's not plausible that these are the same. Now we get to the second part of the question, which is if not, which is the case here, interpret the confidence interval. So this is plausible values for mu sub t minus mu sub c, which we've said is plausible values for the difference in mean improvement times among individuals in a population similar to this sample between playing Nintendo Wii and not playing Nintendo Wii. So I'm going to try to write that down in a way that is a little simpler and makes sense, so that at least in a hypothetical population that is similar to our subjects, the mean improvement time from Nintendo Wii training is believed to be 21.7 to 123.3 seconds greater than from no training at all. Now, is it reasonable to conclude that Nintendo Wii training caused this difference? That's a very different question, and for this we have to think back to section 1.3. Anytime we have questions about causality or about whether it's reasonable to generalize to the population, we have to think all the way back to chapter 1, where we had a diagram. In section 1.3, we saw this diagram. First question, was the sample randomly selected? If so, we can generalize to the population. Was the explanatory variable randomly assigned? If so, we can make conclusions about causality. This question is about causality, so we're interested in the second question. Because our sample wasn't randomly selected, we really can't generalize to the whole population of all medical residents here. We have to have some caveats about who our population really is. But in this case, our explanatory variable is randomly assigned, because if we go back up to the description of the study, we see that the medical residents, all 42, were randomly assigned to undergo Nintendo Wii training or no Nintendo Wii training. So because the explanatory variable was randomly assigned, we can answer yes to this. The importance of this is that if we had done instead an observational study in which we just track video game habits and we track surgical skills, it's possible that people with good surgical skills tend to be more attracted to video games, and that maybe the video games weren't really helping, right? There could be some confounding variable that would explain this connection, but because the explanatory variable was randomly assigned, and these individuals did not choose whether or not to play the video games, we can conclude causality in this particular case.